Hello grade 9 students. Welcome to another virtual class. I am Miss Madhu Vadge. We are studying chapter 8, Quadrilaterals. So far in the chapter we have studied different types of quadrilaterals and properties related to its sides, angles and diagonals. And we applied these properties to answer the questions of exercise 8.1. The second section of this chapter is based on midpoint theorem and its converse. In today's video lesson, we will prove this theorem and also prove its converse. And then we will apply this theorem in answering questions of exercise 8.2. This is theorem 8.9 in the chapter. According to this theorem, the line segment joining the midpoints of two sides of a triangle is parallel to the third side and half of it. It is very important to understand what data is given in the statement and what data is to be proved. So let us separate these two from this statement. The line segment joining the midpoints of two sides of a triangle. This part of the sentence is what is given to us. What follows after this is what is to be proved. That is, we have to prove that this line segment is parallel to the third side and half of it. So now we have to draw a figure for this statement. So we start with what is given, that is a triangle. So consider triangle ABC. In this triangle, we have to mark the midpoints of two sides. So let the midpoint of AC be D and the midpoint of CB be E. The line segment joining the midpoints of two sides. So that line segment is DE. So let's write down what is given. We are given triangle ABC, in which D is midpoint of AC, E is midpoint of BC. What do we have to prove? That DE is parallel to the third side. Since the midpoints are marked on AC and CB, the third side will be AB. So we have to show that DE is parallel to AB and half of it. That is, DE is equal to half AB. In order to prove this theorem, we will have to do some construction. We will have to draw a line from B such that this line is parallel to AC. And then we will extend DE so that it meets this parallel line that we have drawn at point F. In order to prove this theorem, we will start by proving triangle CDE congruent to triangle EFB. In these two triangles, DCE and triangle BEF, clearly CE is equal to EB, as E is the midpoint of CB, which is given. These two angles are equal. Let's mark these angles as 1 and 2. So angle 1 is equal to 2 as they are vertically opposite angles. And we can mark angles C and angle FBE equal. Let's mark these angles as 3 and 4. Why are they equal? Because we have drawn BX parallel to AC. So if we take CB as the transversal, then angle 3 and angle 4 form alternate interior angles. So with these steps, we have shown that in these two triangles, two corresponding angles and an included side is equal. Make sure to write the correct order. So triangle DCE will be congruent to triangle FBE by angle side angle. So if the triangles are congruent, then their corresponding parts are also equal. So we can imply that DE is equal to EF, and we can also say that DC is equal to BF. But we know that DC is equal to AD. This is given as D is midpoint of AC. So in these two equations, the terms on the left hand side are same, so we can equate the right hand side. So we get BF equal to AD. But BF is parallel to AD by construction. So in this quadrilateral DABF, we have AD equal to BF now, and we have AD parallel to BF. So that means in this quadrilateral we have one pair of opposite sides parallel and equal. That means this quadrilateral is a parallelogram. We can mark these steps as 1, 2, 3 and this step as 4. So this is from 3 and 4. And we know that in a parallelogram, both pair of opposite sides are parallel and equal. This means that we can write the other pair of opposite sides, that is AB and DF, parallel and equal to each other. So AB is parallel to DF and AB is equal to DF. Let's mark this as 5 and this result as 6. Now from 5, we can write DE is parallel to AB because DE is part of DF. So if DF is parallel to AB, then DE will also be parallel to AB. So this proves the first part of this theorem, that the line joining the midpoints of two sides of a triangle is parallel to the third side. We have shown these two triangles congruent and therefore DE equal to EF. So this implies that DF will be equal to 2 times DE. But DF is equal to AB. This is from 6. So now we can equate AB to 2DE because the left hand sides are same. So this implies DE is equal to half AB. So we have proved both parts of this theorem. The same theorem can be written in converse, which is given as theorem 8.10 in this chapter. The statement for converse is the line drawn through the midpoint of one side of a triangle parallel to another side bisects the third side. So let's consider a triangle ABC. In this triangle, a line is drawn through the midpoint of one side. So let's say midpoint of AC is D. From this point D, we have to draw a line such that this line is parallel to another side. So let's say this line DE is parallel to AB. We have to prove that this line bisects the third side. That means we have to show that CE is equal to EB. So we are given triangle ABC in which D is the midpoint and we are given DE parallel to AB. We have to prove that E is the midpoint of BC. That means we have to show that CE is equal to EB. In order to prove the converse statement, we will have to do the same construction, that is from point B, draw line BX that is parallel to AC and then extend DE to meet this line at F. Now observe quadrilateral ABFD. In this quadrilateral, AB is parallel to DF. What we are given is DE parallel to AB, but DF is an extended version of DE. So we can say that DF is parallel to AB. And by construction, we have AD parallel to BF. That means ABFD is a parallelogram. Using the properties of a parallelogram, we can say that the opposite sides are equal. So this implies that AD is equal to BF. But AD is also equal to DC because D is the midpoint which is given. So this implies that DC is equal to BF. So now we can prove these two triangles congruent. We have vertically opposite angles equal, and these two angles will also be equal because they are alternate interior angles. And we have just shown that DC is equal to BF. So by angle side criteria, these two triangles will be congruent. And if they are congruent, then CE will be equal to EB because they are corresponding parts of congruent triangles, and therefore E is the midpoint of CB. I have explained the proof for converse step by step. So now it will be easy for you all to write the proof as an assignment. Let's proceed further and apply the knowledge of midpoint theorem in answering questions of exercise 8.2. ABCD is a quadrilateral in which P, Q, R and S are midpoints of the sides AB, BC, CD and DA respectively. AC is a diagonal. We have to show SR is parallel to AC and SR is equal to half AC. PQ is equal to SR and PQRS is a parallelogram. We are given that P is midpoint of AB, Q is midpoint of BC, R is midpoint of DC and S is midpoint of AD. What we have to prove is clearly listed pointwise. Consider triangle DAC. In this triangle, S and R are midpoints of two sides. So using midpoint theorem, the line joining these midpoints will be parallel to the third side, which is AC, and will be half of it. So start by mentioning the triangle in which you are applying the midpoint theorem. So in triangle ADC, S and R are midpoints of DA and DC. So this implies SR is parallel to AC and SR is equal to half of AC. Let's mark this as 1 and this as 2. Now we will consider triangle ACB. In this triangle, P and Q are midpoints of two sides, AB and BC. So line joining these 2 points, that is PQ, will be parallel to the third side and half of it. Let's mark these results as 3 and 4. So from 1 and 3, we have AC parallel to SR and AC parallel to PQ. That means SR and PQ are parallel to the same line. Therefore, they are parallel to each other. So this implies PQ is parallel to SR from 1 and 3. And from second and fourth result, since the right hand sides are equal, we can equate their left hand sides. So this implies PQ is equal to SR, and that is what we have to show in the second part. Let's mark these 2 steps as 5 and 6. In this quadrilateral PQRS, we have shown PQ equal to SR and PQ parallel to SR. So we have one pair of opposite sides parallel and equal. This implies that PQRS is a parallelogram. Now question number 6 of this exercise will have exactly same answer as the first one. Let's see how. Show that the line segments joining the midpoints of the opposite sides of a quadrilateral bisect each other. So we have a quadrilateral ABCD in which joining the midpoints of opposite sides we get line segments PR and SQ. Also, if we join these midpoints in an order, we get a quadrilateral PQRS. Notice that PR and SQ are the diagonals of this quadrilateral. And we have studied that diagonals of a parallelogram bisect each other. So all we need to do is prove that PQRS is a parallelogram. After answering question number 1, we already know how to show PQRS as a parallelogram. So we will follow exactly same steps as we have done for question number 1. And once you show that PQRS is a parallelogram, it will imply that the diagonals bisect each other. So the answer for this question is to be written as assignment. With this, we come to the end of this video lesson. Your assignment is to learn the midpoint theorem, write down the steps to prove its converse, and write the answer for question number 6 of exercise 8.2. See you in the next class. Until then, goodbye.